So I'm looking at an old exam. I want to find these points on the chi-square distribution. So if you have a 90% confidence level, that means alpha is 5%. Splitting that 5% up into two parts, you're going to get chi-square sub r and chi-square sub l. Your degrees of freedom is going to be 1 minus n. Since we had n equals 29 values, we had 28 for our degrees of freedom. Let's go to StatDisk for this. Probability distributions, and I believe you called it chi. All right, so degrees of freedom, 28. It's chi. It's chi. You're just doing that to annoy me. Area to the right of our chi-square value. So there's a couple things we want. We want to find 2.5% of the area in the left tail. That's going to be 97.5% of the area to the right of that. So I'm going to put in 0.975, and I get a value of 15.3 for my chi-squared. All right, so that's chi-square sub L, 15.3. Let's do chi-square sub R. How much of the area is going to be to the right of this?
Will it be the same?
No, it's not going to be the same. How about 2.5%? So I'll change that to 0.025. Now, should my value here be bigger or smaller than my value here? You're to the farther to the right. Our number is getting bigger or smaller as I move to the right?
Bigger.
Bigger. So I expect a bigger number when I do this one, and I'm rewarded. 44.5. If I needed a specific number of digits on an exam, I would tell you.
So, okay. So how do you find it? Yeah, that's what I was about to say. If it's 0.025 in both sides, and that's what we're finding.
What's the total area underneath our distributions? Chi-square distribution, t-distribution, normal distribution. The total area is 1. So if 1 is the total area here, and 2.5% is to the left, then 97.5% of the area has to be to the right. And same thing here. 2.5% is in the right tail, 97.5% is to the left of that.
Okay, so can you go back to StatDisk then?
So you did 1 minus 0.2.
Oh, okay.
0.025?
Okay. Because it asked
Yeah.
specifically for the area to the right.
Yeah, it's asking here, what's the area to the right? So for chi-square sub r, that's just what it looked like. Oh, well, I want 2.5% of the area to the right, so that's my chi-square sub r. For chi-square sub L, if 97.5% of the area is to the right, that means that little bit is to the left. So that's going to be 1 minus 97.5%, which is going to be my 2.5%. Or 1 minus 2.5% is going to be the 97.5%.
Okay.
Alright, I got you.
975. Was there any other ones on this one that is bothering you? All right.
Can I have it?
All yours.
Thank you. Oh, this was just a quick question about this. I didn't know if it had 2 options. Question.
What assumptions do you have to make in order to create the confidence interval above? So this one was a confidence interval for a standard deviation, I think. No, mean level of attractiveness. In this case, the additional assumption that you had to make is that this data are normally distributed. All right, and we have to make that assumption because our sample size isn't large enough. There's one of 2 assumptions you have to make. Either n is greater than 30, or the population is normally distributed. So one of those 2 have to be true. Now, certainly the population or the sample size isn't greater than 30. So the additional assumption that we have to make is that the population is normally distributed. That may or may not be the case. I certainly haven't studied this kind of data to know. And one last one, right?
Yeah. You mentioned it briefly, and I forgot exactly what you said. This one. That was what was on your answer key, at least.
Yeah, we didn't do bootstrapping this semester, so we don't have to worry about that one. It's a different way to make a confidence interval, but we haven't covered bootstrapping, so we're okay. Yes?
On that study guide, is there anything else that we should worry about that's not on there? And is there anything else
There
on
could
there?
be. I mean, you're responsible for everything we've covered since section 6.5, which would be normality test. So let me go through a few things myself that I wanted to mention. And I wanted to start out with something that's kind of related to what we're going to do later in this course, and that is we're going to talk about, where is it? We're going to talk about proving causation right here. So on the 17th, so 2 weeks from today, we're going to talk about proving causation. And one of the things that you can do to prove causation is try and establish a better cause and effect relationship through a lot of repeated studies saying the same thing, getting the same kind of answer again and again. And one way to kind of bind all those things together is something called a meta-analysis. So let's talk about a meta-analysis in the context, where is it? Yeah, this one. So my dad sent me an article over the weekend about getting your energy up. A lot of people who, when they're old, unlike me, suffer a problem of feeling fatigued. Now, if you did a Google search on meta-analysis, they'd come up with this definition for you here. Basically, what you're doing is you're combining the results from multiple studies to try and have a larger sample size and therefore learn a little bit more than you would otherwise. Now, remember what happened just a little bit ago when we were talking about our confidence intervals. So our confidence intervals, we did mean to proportions. Let's just take a look at some easy numbers here. So we've got two samples, both sides 100. One has a 10% success rate, the other one has a 15% success rate. And here's our confidence interval. What if I just doubled these numbers to 200 and then 20 and then 200 and then 30? Now let's take a look at our size of our confidence interval. It was, let's see, let's do that. Let me put it here. This is what it was, and this is what it is. So our confidence interval is going to get narrower when you have a larger and larger sample size. That was a big thing that we talked about. Let's double this one last time. So 440 and then 460. And we'll copy both of these. And let's look at this one last time. What's happening to your confidence interval? It's getting narrower and narrower and narrower. So that's a good thing. You're getting more and more information from your population or from your data. Now, what we're overall trying to find is an estimate of our parameters. So let's think about the different parameters that we have. So parameters and statistics. Actually, I should probably write it the other way around. I like writing it the other way better. Statistics and parameters. We've dealt with several so far for our mean, standard deviation, and proportion. what were these statistics? What are our statistics for a sample mean? X bar. Sample standard deviation? S. Proportion? P hat, thank you. And then over here for parameters, mu, sigma, p. All right. These are trying to estimate these. And you get better estimates with increasing sample size. So as sample size increases, the width of your confidence interval will shrink. Confidence interval will shrink. And that's a good thing. Now you can write your confidence interval in a couple different ways. So in particular, if you follow some of the links for this story here that I was referencing, they had a confidence interval for the number or the percentage of adults over 60 who described themselves as feeling easily fatigued. Okay, so that confidence interval, if you look it up, would be something like this. So confidence interval, put 95% confidence interval for percent of adults who feel fatigued. And that confidence interval is 49.2% is less than P is less than 67.2%. Okay, let's draw that out and try and understand that in a different way. Let me draw this on a number line. Now notice in the middle here, I've got P and not P hat. Why do I have P and not P hat? We're trying to estimate this value. We don't know what it is. That's why we're taking a sample. So we're saying that the true value is somewhere in here. So somewhere between 0.492 and 0.672. So this is in the middle. This is your P hat minus some error and P hat plus some error. What they haven't given us is what's actually P hat. What's the proportion of, people who feel fatigued according to this study? How would you find P hat? What would I do there? Average the two, yeah. Average 2. So P hat, let's do that over here. P hat equals 0.492 plus 0.672 over 2. What am I going to get for P hat? Well, I guess I'll find out over here. Oh, let me do it this way. 0.492 plus 0.672 divided by 2. All right, so 0.582.
I said that.
So that's your best estimate, is 0.582. What does that mean E is? E is that distance from here to here. That distance is E, or this distance is E. That's how far you're going from your P hat. So what is that distance? How far is that? What would I do, or what could I do to find that distance that represents E? I'm not sure why more of you aren't taking notes. This is on the test on Wednesday, so just so you know.
What is subtracting? I'm about to say, are we subtracting?
Yeah, that'd be one way. Sure, subtract, right? 0.672 minus 0.582. I think that's 0.09.
And then the other way, do we add?
You're not going to be able to get E by adding.
Not add.
The other possibility is you could take this minus this, but that's twice E, right? You're going to have E here and E here, so you can take the difference of these two and then divide by 2. That would work. So either way. Now, rewriting it like this allows me to rewrite the confidence interval in a different way. And one way that you'll see confidence intervals written sometimes is p hat plus or minus E. And I kind of like this because it's telling you what your best guess is. Your best guess is your point estimate. That's going to be 0.582 plus or minus 0.09. So that's an alternative way to write your confidence interval. The benefit here is that you can easily see what's in the middle. It's like, okay, that's my best guess. That's my point estimate. Plus or minus, a little error term.
So this down here in red is how we find what our
That's how you can find E, yeah. And then you can rewrite it, your confidence interval like that. Sometimes you'll get a confidence interval like this. If you want these numbers, you just take this plus 0.09 and this minus 0.09 will give you those two other values. So you can go back and forth between these. It's kind of a little preference thing, what you prefer. But, you know, certainly, I guess what you can take from this is I'm taking the time to remind you of this now, 2 days before a test. So think of that what you will.
Okay, and then you said the other option would be 0.672 minus 0.492 divided by 2.
Yep. If you have those two numbers, if you subtract them and divide by 2, you'll get E, just like we did by subtracting the middle number.
Okay, and this is called, we're finding the confidence interval, right?
We're just changing forms of the confidence interval. Here you've got p hat minus E, p hat plus E. That's your confidence interval. That's what we did here. You could also write it like this. So there's, A and B. There's 2 different ways to write your confidence interval. It's just a matter of which one is being asked for.
Yeah, so I guess that's what my question is. So on the exam, how do I know that this is what I'm doing? Like, what would the question look like?
I might give you one of these and ask for the other one. Or, yeah, that would be it. If I gave you one, I might ask for the other one. That'd be all.
Okay.
It's not meant to be a hard problem. Christine?
For B, why is it p hat instead of p?
Because this is our best guess. We're trying to figure out where this is. We don't know what P is. We couldn't add E to P because we don't know what P is. The only thing we can add P to is, or E to is our best guess, which is P hat.
Then we apply that to the actual p.
Yeah, and this is our confidence interval for the actual P, which we don't know what it is. Speaking of confidence intervals, let's play around with one. A group of morning cyclists. Let's see, how do I want to write this? Have an average heart rate of X bar equals 136.7 with standard deviation of 12.9 and n equals 21. Find and interpret a 95% confidence interval. So find and interpret a 95% confidence interval. Okay, easy enough. Let's work on that for a moment. Well, let's see. We're kind of running short on time here, so maybe I'll help out. a little bit on that one.
That's 12.9.
12.9, yes. Thank you. 12.9. If you plugged in this data, you would plug it into StatDisk, right? You plug it in, you go to confidence intervals underneath analysis, mean one sample, plug it all in and evaluate. Now, you're never going to be plugging in the standard deviation. You don't know what the population standard deviation is. In this case, we end up with a confidence interval between 130.83 and 142.57. So 130.83 less than mu less than 142.57. We can be 95% confident that the true mean heart rate during morning cycling is between 130.83 and 142.57 beats per minute. BPM. Should be.
Because I got 130.12 and 141.8.
I'm not going to try and figure out where that difference would be. But I do have kind of a follow-up question for you. Suppose in another workout, you find that your heart rate was 149. Does that mean that that ride was significantly harder than your usual ride? Why? It's outside your confidence interval, yeah. So if you were doing a hypothesis test, you could be rejecting depending on how things are set up there. But yeah, it definitely looks like it's harder than your usual one. Last but not least, and I'll just have to scan these in the notes and go over those with you. I also promised that I would tell you what a type 1 and type 2 error is. These are the definitions you'll see on the exam. Type 1 error is rejecting H naught when it's true. So that's an error. You shouldn't be rejecting it when it's true. Or if you fail to reject H naught when it's false. So let's go back to our cycling example. Suppose that your null hypothesis is that your heart rate is 136 beats per minute during morning cycling. What's going to happen when you make a type 1 error? Well, this is true, but you reject it. I need to see both pieces of information. I need to know if H naught is true or false, and I need to know what your decision is in comparison to that. So, in this case, if you're making a type 1 error, is this true or false? It's true. So we'll start out that way. Type 1 error. Well, it's true that the heart rate during morning cycling is 136 beats per minute. The data reject that claim. So you tell me what's true, you tell me what your decision is. Let's look at a type 2 error. Type 2 error, this is false, but you fail to reject it. So one way you could word a type 2 error, say, well, it is true that your heart rate is 136 beats per minute during morning cycling. The data rejected that claim. So, okay, it's true, but you reject it. Wait a minute, that doesn't look right. Oh, that's type 1. Yeah. Wait a minute, I was reading type 1 again. My bad. Well, it's not true that the mean heart rate during cycling is 136. So you're saying that this isn't true. The data failed to reject that claim. So it's not true, but we didn't reject it. So there's your type 2 error. Now, there's a lot of different ways you can state those things, just as long as you're telling me the two things I want to know. If H naught is true or false, and what your decision was that made it a type 1 or type 2 error. Okay, anything else? Ben? Sure. I'll scan these in and put them in the notes.
I just want to see the type 2 error definition.
Oh, the type 2 error definition. Fail to reject H naught when it is false. Okay, have a good one and see ya.